Okay, students, we are in the next lecture of the RRE series. Okay, in this lecture, we are going to complete the ionic equilibrium chapter in one shot. As in our regular lectures, we are going to complete from the very basic to the advanced level of information. And this lecture, I am anticipating to be a lengthy one. So try to take a break after around half an hour or 15 minutes, but come back to the same level and come back, make a notes and maintain the same amount of interest till the last. Okay. This is very, very scoring chapter. Every time there will be definitely a question. Let it be any exam. Irrespective of type of exam, there will be a definite question from this topic. So that's why I wanted to see this video at least 2 to 3 times with the full tempo. Okay, full attentiveness. Don't lose your attentiveness. Don't stop watching after 10 minutes or 15 minutes. If you feel, you take a break and then you continue. Okay, so ionic equilibrium in one shot, the most important chapter and most difficult chapter, but I will try to make it as the easiest possible way with my explanation. Okay, are you ready? So here the very first beginning topic in the ionic equilibrium is Ostwald dilution law. Okay, so in the Ostwald dilution law, it is applicable for weak electrolyte like weak acid and weak bases. It is applicable for weak acid and weak base, and it is applicable during diluting. Okay, so for example, I'm taking HA. HA is a weak acid. A is any anion. Okay. And it is a monoprotic acid. It is diluted. Then it will give as a H3O positive plus A minus. Okay. So 1, 0, 0, 1 minus alpha, alpha, and alpha. Okay. So these are the some alpha values. So, but it is possible alpha is determined for one molarity only, one unit concentration. Okay, but if you have more than one unit concentration, less than one unit concentration, it is to be multiplied. Okay. So as a normal equilibrium constant, it is second part of the equilibrium. But here we are going to deal with the ions. That's why it is called as a ionic equilibrium. Equilibrium constant for this reaction is going to be concentration of H3O plus, concentration of A minus, concentration of A minus divided by concentration of HA into concentration of H2O. Okay, this is normal equilibrium only. But here, when you cross multiply this Kc into H2O, then this is going to be, see here in this place what I can write, C alpha, in this place also C alpha divided by 1 minus C alpha. Okay, so C into 1 minus alpha. Is it understood, students? So this is for the numerator and this is for the denominator. Okay, so for the denominator part, what I have done, this cross multiplied constant into constant, it is going to be a new constant that is called as a Ka. A stands for here acid. Okay, and C square alpha square divided by C into 1 minus alpha. Okay, C into what? C square into alpha square, C into 1 minus alpha. Okay, C and C will get cancelled. Then you will get a final equation. Okay, final equation I am writing it as here. Ka. Ka is equal to C alpha square upon 1 minus alpha. This is the first formula we have derived. So keep a note of the every formula. This chapter is mostly formula based. Ka is equal to what is the formula? C alpha square upon 1 minus alpha. Okay. So for this in future, we are going to use it in the different forms. Okay. So what is the direct forms we are going to use, where it is used, that I am going to tell you. Okay. Now, but alpha is very, very, very less than 1. Then this will become as a Ka is equal to C alpha square, second formula. But it is to be used only when the given alpha degree of dissociation is very, very less than the 1. Okay. Then next formula, alpha is equal to square root of Ka upon C. Okay. This is the third formula. See how many type of formulas we are getting. from the very first formula. But if you understand first formula, then it is easy for remembering other parts also. Okay. Now in the derivation, I told you H3O positive is equal to C alpha or not. So C alpha, in place of the C alpha, what we can write, square root of Ka upon C. So that means square root of Ka into C we can write. On simplifying, we'll get square root of Ka into C. Okay. So this we are going to use afterwards. Presently, I'm telling you the formula, but we are going to use it afterwards. Okay. Concentration of H3O positive is equal to square root of Ka into C. Okay. This formula, this formula, this formula, this formula. Try to write it with your name. If not, at least take a screenshot of it. Okay. And all formulas of the ionic equilibrium are very, very much important. Okay. Now, this is for the acid. Same way you can make it for the base also. Okay. So here what you will write, Kb. Here what you will write, Kb. Here what you will write, Kb. Okay, base. B stands for base, A stands for acid. Okay. Now there what you will get here, in place of H3O positive, what you will get there, OH minus. Concentration of OH minus will be C alpha. Okay. And here what you will get, Kb. So here what you will get, OH. Okay. So OH minus will be square root of Kb into C. Is it understood? So square root of Ka, in place of square root of Ka, it is we have to take Kb. All the six, 1, 2, 3, 4. Four formulas, if you understand for acid, then need not to worry about the base. Same thing you can just copy, paste and modify it for bases also. So you don't need not to worry much about the Oswald dilution law. This part I am going to use it afterwards. Are you ready with me? Okay. Okay, now we are into the next segment, acid-base concepts. Okay, so I am giving you just a summary and comparative studies so that in very short span of time you should be able to understand all concepts thoroughly. Okay, so there are three concepts which are more important for the examination point of view: Arrhenius concept, Bronsted concept, and Levis concept. And there are some common points among them. Okay, so acid, base, and neutralization. According to Arrhenius, the substance which furnishes H positive in aqueous solution, okay, in which solution? Aqueous solution are called as a acid, okay. The substance which furnishes OH minus in aqueous solution are called as a base, okay. And any substance which any reaction in which H plus from the acid, OH from the base, H plus from the acid, OH from the base combine together to form water is called as a neutralization. Is called as what? Neutralization. These are the key points of the Arrhenius concept. Okay. Then coming to the Bronsted concept. In Bronsted concept, according to Bronsted acid is a substance which donates. Okay, which donates proton. Okay, proton is nothing but H plus only, but he changed the word. Okay, in place of the H plus, what he told the proton. Okay, so donates proton and the substance which accepts proton. Okay, so accepts proton is called as a base, and the substance, this is a transfer. It is simply neutralization is what? Transfer. Okay, transfer of what? Proton. From where? Proton from acid to base. It will start from acid and it will reach to what? Base. It will reach to base. Okay. Then coming to the Levis concept. In the Levis concept, it is entirely different. At least these two are same. Okay. There is a question. All Arrhenius acids are Bronsted acid, but all Arrhenius bases are not Bronsted base. It is definitely when you compare the sentences, it will be, you will be able to understand. Okay. So in the Levis concept, the substance which accepts, okay, which accepts lone pair of electrons is called as acid. The substance which donates lone pair of electron. Which donates lone pair of electron is called as base, and the substance, it is just formation. What it is? Formation of coordinate covalent bond. Okay, formation of coordinate covalent bond. Okay, formation of coordinate covalent bond is called as a neutralization. According to Levis concept, neutralization is formation of coordinate covalent bond. Okay, so these are the three different concepts. These are the three different acid-base concepts, and I have given a comparative study. Okay, so individually we are going to study in depth. Okay. Okay, now we are going to study in-depth study about the Bronsted concept. Now we are going to study in-depth study of the Bronsted concept. Okay, so Bronsted concept depends upon the conjugate acid-base pair. What is the topic? Conjugate acid-base pair. Any pair of substance which differs by one H plus are called as conjugate acid-base pair. Any substance which differs by one H plus are called as conjugate acid base pair. Okay, so let us take an acid Ha. As it is acid, it will lose H plus and left over with the A minus. So this A minus and this Ha, they both differ by one H plus. Then that pair of Ha and A minus is called as conjugate acid base pair. Okay, so there are certain substances which can donate as well as accept H plus. Such substances are called as amphoteric. What it is? Amphoteric. Okay. So once they lose H plus, okay. So loss of H plus is called as acid. In this direction, it is acid, and the substance whichever is formed, like this is losing H plus, substance which is formed is a base. So base, acid, acid and base. Okay. So sometimes it may gain H plus also. That's why it is called as amphoteric. Okay, substance which can act as a both acid as well as base. So once it gains the same substance behaves as a base, the originated product, the resulted product is called as a acid. So these are also acid base pair. This is also acid base pair, but in this pair it is acid. In this pair it is base. That is the difference between the conjugate acid base pair. Is it understood, students? So are you making notes? So try to make notes and try to revise it at least two times. This is the most important chapter. Okay. Now, suppose this is strong, its conjugate base is going to be weak. If conjugate base is strong, then conjugate acid is going to be weak. Either acid can be strong or base can be strong. If one is strong, another will be automatically weak. Conjugate acid of a strong base is weak. Is it understood? That is the formula about the Bronsted concept. Okay. And one more thing, suppose Ka is dissociation constant of acid and Kb is dissociation constant of base. Okay. So on multiplying both of them, you are going to get Kw. Okay. What is Kw? You will come to know. But Ka into Kb for conjugate acid base pair is equal to how much? Kw. Okay. So this is all about the Bronsted concept regarding the conjugate acid base pair. Okay. Are you ready for next segment? Okay, we are into the very important next segment, that is Levis concept. We are into the very next segment, that is Levis concept, and in the Levis concept we are going to study mainly focus on the examination oriented points, types of acid and bases. Okay, so in that also specifically speaking types of acid is more important. Okay, so as it is a RRU series, as a one chapter, one day or one period, one lecture. That's why I am focusing only on the examination oriented questions only. Okay. So for detailed studies, you have to go through the individual lectures. For lecture of Levis concept separate like that. Okay. It is just a general idea and it is highly scoring. If you attempt, then if you listen to this video properly, then you are going to score good marks. Okay. Let us start into the acids. All cations. So as I told you, acids are lone pair acceptors. Any substance which accepts lone pair of electron are called as acids. So all cations, that means all positively charged ions are acids. Okay. Second one is all molecule with, for example, K plus, okay, Al3 plus, Mg2 plus. Here, these are some examples of all cations. Okay. So obviously they in the base side, I think you can write to here. Okay. Now second one is here what will be the answer? All anions. Okay. What will be the answer here? All anions, negatively charged ions. Then second comes all molecule with electron deficient centers. Okay. So let us take B. Cl3. What is the answer? BCl3. In BCl3, boron have only 6 electrons. Okay, still it could not gain the octet. Such type of molecule, what they will do, they will accept the lone pair of electron. And most important organic reagent, Friedel-Crafts reagent. What is that? Anhydrous AlCl3. This is also example of Lewis acids. Okay. So these are the some examples where they cannot form the octet. Even after trying completely, they could not confirm the octet. Here, electron deficient center, here it is going to be electron rich center like NH3. Okay. NH3 after octet, still it possesses one lone pair. Okay. Then all molecule with pi bond and higher electronegativity outer atom. Okay. So this requires some explanation. So try to listen carefully. C double bond O and C double bond O. This electronegativity should be more than this. Then only it is called as acid. If they both are same electronegative, then it comes under the base. Like alkenes are bases. Alkenes are not acids. Alkenes are bases. Terminal alkynes are acids because of the H plus. Okay. So this is the pi bond. Understood? Now, because of this, what happens? This go this side, this will come this side, positive and negative. Okay. So positive will be accepting the lone pair of electron. A molecule with pi bond, listen very carefully, with the electronegativity of higher at other atom should be higher one. Okay. Then third one, molecule with empty d orbitals. Molecule with empty d orbital like SiCl4. Okay. For this example, I am writing here SiCl4. Okay. In SiCl4, even the octet is fulfilled, octet is over already, precise, it is electron precise, but still it can accept the electron and keep it in the d orbitals. Okay. So these are the four types of acids, and accordingly three types of acids only. Fourth type is not there in the base. Okay. So here, like pi bond is there, but electronegativity of both atoms should be same. That pi bond electron will be donated, and that time it will act as a base. Is it understood, Levis concept? Okay. Okay, we are into the next most important widely used concept, Arrhenius concept, and it is used for pH scale. Okay, so entire pH scale is depending on a topic called as ionic product of water. Okay, ionic product of water is denoted with Kw. As of now, we have seen the third constant. Okay, Ka is dissociation constant of acid, Kb is dissociation constant of base, and this is the Kw. Because lot of formulas are about to come, so be in between also we should be able to revise it thoroughly. Okay, so ionic product of water. Okay. Now, water ions are two ions, that is H plus and OH minus. Their multiplication is called as ionic product of water. Okay, and at 25 degree it is 10 to the power of minus 14. This is an experimental value, so there is no logic how it came. Okay, it is calculated at room temperature of 25 degrees Celsius. They determine how many H plus are there per liter, how many OH minus are there per liter, then multiplied, then they got 10 to the power of minus 14. If you increase the temperature, this Kw will increase because it is an endothermic process. Okay. In endothermic process, dissociation will be increasing, number of ions also will increase. Okay. So for pure water, if you take water pure, that is nothing is mixed, no acid, no base is mixed, then equal number of H plus, equal number of OH minus. So 10 to the power of minus 14, when it is distributed, it is going to give you 10 to the power of minus 7 moles of H plus, 10 to the power of minus 7 moles of H plus per liter. Okay. But if you add acid, then H plus will increase. Correspondingly, there is a decrease in OH minus, because on multiplying this has to be 10 to the power minus 14 only. Because in the equilibrium chapter I told you, equilibrium constant is constant at constant temperature. Okay. So if one increases, automatically other will decrease, because this is constant. Okay. If it is increasing 10 times, it will decrease by 10 times, into 10 by 10 will be again 10 to the power minus 14. Okay. So same way, H plus less than OH minus when base is added. Base added means you are adding OH minus. So OH minus increases 10 times, H plus will decrease 10 times, decrease and increase will compensate and will give you 10 to the power of minus 14 at 25 degrees Celsius. Okay. Okay, as we are continuing to be Arrhenius concept only, and we are going to study about the pH scale. It is an application part of the ionic product of water only. Okay, so from ionic product of water, if concentration of, suppose pure water, if you are taking, concentration of H plus is going to be 10 to the power of minus 7, and concentration of OH minus also going to be 10 to the power of minus 7. So when you apply negative log to it, you will get pH. When you apply negative log to it, you will get pOH. Okay. So for pure water, this is the complete information. Both acid and base will have same pH and pOH. Both concentration of H plus and OH minus will be same. Okay. And but apart from this, this is the when you are increasing or decreasing. Suppose here we are increasing the concentration of base. Accordingly, there will be decrease in concentration of acid. So there is a decrease in pH. Sorry, increase in pH. Okay. When concentration of H plus is increased, pH will concentration decreased, pH will increase. Concentration increased, pH will decrease. pH is inversely proportional to concentration. Okay. How it is mathematically, I will show you. You must have studied pH is equal to negative log of H plus. Okay. So with this formula, students have wrong impression that concentration pH are directly proportional. Okay, so for those students, I will write it as a log 1 upon H plus. Here this minus 1 when comes over here, H plus to the power of minus 1 can be written as 1 upon or not. So pH and concentration of H plus both are inversely proportional. Higher the concentration, lower will be pH. Same is the case with the pOH and OH minus. Higher the concentration of OH minus, lower will be pOH. Okay. So this is the concentration. Okay. pH, pOH. See here, it will be keep on increasing. Up to where it will increase? Up to maximum 10 to the power of minus 14. So it can be 14. pH scale ranges from 0 to 14. At 7, both acid and bases are strong, both are equal, therefore it is neutral. Okay, so don't think that higher pH means strong acid. Lower pH is strong acid, lower pOH is strong base, higher pOH is weak base, higher pH is weak acid. Keep it in mind, and it is 10 times. If you increase the concentration by 10 times, but pH is going to increase by 1. All of you make a note of it. If you increase the concentration by suppose 100 times, okay, but pH is going to increase by 2 only. Okay, so if you increase by 100 times, it is going to be plus 2. Okay, if you divide it by the 100 times, it is going to be minus. Okay, so if you decrease by 100 times, divided by 100 times, pH is going to be minus 2. If you multiply by 100 times, it is going to be plus 2. Same way with the multiply by 1000, pH is going to be changed. Okay, accordingly there will be change. Is it understood? Okay, this is an example. Okay, for example, concentration of H plus. Concentration of H plus is initially 10 to the power of minus 3. Okay, so on dividing, okay, I will tell you, if on dividing by 100, okay, pH increases by 2. Okay, dividing by 1000, pH increases by 3. This concept, dividing, increase, multiplying minus, but not same time. Number of zeros, two zeros, two increase, two zeros, two, three zeros, three increase. Divide will increase and multiply will decrease. Okay. So 10 to the power of minus 3 divided by 100. Then you will get 10 to the power of minus 5. So initially pH was how much? 3. Now pH is how much? 5. So concentration when divided by 100, pH is increased by 2 times. Is it understood? This concept is lot of importance. Okay. Okay, after the pH and its applications. After the pH and its application, we are into the very next formula, next topic, solubility product. Okay, so as it is for the acid, it is dissociation constant of acid Ka. For base, dissociation constant of base Kb. For water, dissociation constant of water Kw. That is called as a ionic product. Similarly, for salts, there is a new constant that is called as a KSP, solubility product. Okay, so it is applicable only for the sparingly soluble salts because most of the salts are completely soluble. Most of the salts are completely soluble, so they will not be reversible. If they are not reversible, there is no chance of equilibrium. There is no chance of equilibrium, no equilibrium constant. Okay, so this is applicable only for sparingly soluble salts. Okay, or some weak acid also you can say, weak base also you can say. Okay, so let us take AXBY. AXBY is a sparingly soluble salt. So X and Y can be anything, even it can be 1 also, like AgCl is a sparingly soluble. X will be 1, Y will be 1. Okay, so PbSO4 sparingly soluble, Pb1 and SO4 also 1. BaCl2, that time X will be 1 but Y will be 2. Al2O3, X is 2, Y is equal to 3. So that can be changed as per your own requirement. That's why I have taken as a general value XY. Okay. So AXBY is a salt when dissolved in water. Then it dissociates to give X moles of A. Its charge is generated by the next one. Okay, here it is a charge deciding, here it is a charge deciding. Okay, so X into A to the power of Y plus, same way Y into B to the power of X minus. Okay, so these many moles it is generated. Number of ions will be X, but charge on ion will be Y. Same way number of ions will be By, but charge on the B will be X minus. Okay, so if 1 mole it is dissociating, it is going to generate X moles S and Y moles S over here B. Okay, Y moles of B. So S is number of moles per liter. Okay, so then equilibrium, normal equilibrium constant if is formulate product upon reactant. Okay, so here product is A y plus to the power of x, B x minus to the power of y divided by ax by divided by what? Ax by. Okay, so Kc, what is Kc here? Equilibrium constant, and this is constant. Okay, because it is a solid. So solid concentration is constant, and this side it is almost negligible. So if you take initially 1 mole, it is going to be 1 mole almost here are 0.99. So it is constant into constant, new constant Ksp. Okay, so Ksp on simplification. This is also most important formula. X to the power of x, y to the power of y, s to the power of x plus y. This is about the solubility product. Is it understood, students? Okay, next we are in the next most important topic, that is common ion effect. We are going to study the next about common ion effect. Okay, definition part, it is the decrease in solubility of sparingly soluble salt when another salt having common ion added to it. Okay, so here I am taking two examples. This is sparingly soluble, this is completely soluble. Okay, so when you add completely soluble salt to the solution of sparingly soluble salt, its solubility is going to decrease. It is going to decrease because of what? Common ion. NaCl also gives Cl minus, AgCl also gives Cl minus. And it cannot come back because it is a completely soluble. It is a reversible reaction. Okay. So this is a reversible reaction. Therefore, it will come back in this direction. It will come back in this direction. Hence, what happens? Solubility, number of ions able to give Ag plus and Cl minus will decrease. Okay. So in this part, what happens? Like normally, what we will write KSP. KSP of AgCl is equal to what? Concentration of Ag plus into concentration of Cl minus. Okay, but it is almost completely dissolving. So the Cl minus will be equal to concentration of NaCl. Okay, so now the KSP can be written as concentration of Ag plus into here concentration of NaCl we can write. Okay, because it is completely soluble. If you take it as a 1 molarity, you are going to get 1 molarity. If you are going to take 10 molarity, 10 molarity. Okay, so like that we will neglect this concentration value. Okay, actually what it is supposed to be and what we are writing, I think now it is clear. Okay, so otherwise I will write it here also. So I will write it here. Ksp of AgCl is equal to concentration of Ag plus into concentration of Cl minus. So here it is going to be S and here it is going to be S plus concentration of NaCl. Okay, because this is the major portion. Okay, so this we can neglect. Addition is there and this value is smaller, this value is larger. So KSP is equal to concentration of solubility of AgCl into concentration of NaCl. Okay, suppose here 2 is there, 2 into also you have to do. Understood? So like this it will affect the solubility. This increases, this has to decrease because it is constant. Understood? What is this here? Solubility. Solubility will decrease because its concentration is increased. Okay. So this is what the common ion effect. Okay. But if the same thing happens, if the same thing happens with the sparingly soluble salts of the two sparingly soluble salt. Okay. Suppose there is another example of HgCl. Okay. So this is also sparingly soluble. Then it is going to give you Hg positive Cl minus. Okay. So here also common ion effect only, but it is not called as a common ion effect. There it is called as a simultaneous solubility. What it is called as? Simultaneous solubility. Okay. So here Cl concentration, let us take this is S1, this is S1. So this is S2, this is S2. Okay. Now what is the difference in common ion effect and simultaneous solubility? I am telling you, try to understand it carefully. Now concentration of, sorry, KSP of AgCl. Suppose KSP KSP of AgCl, okay, is equal to what we will write, concentration of Ag plus into concentration of Cl minus or not. Now what we will write, here we can write S1, but here what we will write, S1 plus S2. That is the difference in common ion effect and simultaneous solubility. In common ion effect, we will take only concentration of strong salt. But here, both values are added. We cannot neglect S1, we cannot neglect S2. So both will be added. Same way, KSP of suppose HgCl. Of suppose HgCl, what you will write here, it is S2 into again S1 plus S2. Difference in simultaneous solubility and common ion effect, I think it is understood. Okay. So solubility product, common ion effect, and simultaneous solubility. I think all the three topics are completed and perfect. Okay. Okay, we are into the very, very difficult, very, very important topic that is called salt hydrolysis. Okay, so salt hydrolysis, if you study it in a proper way, then it is very easy. Okay, it is not a new topic, it is simply old topic only. Okay, so if I take suppose acid plus base, then what it will form? Salt plus water. What it is going to give? Salt plus water. Okay, this already equation you have seen it or not? Okay, you have seen. That means same thing only we are studying. But instead of in this direction, we will study in this direction. Okay, acid plus base gives salt plus water. Salt plus water will give you acid and base. Okay, so salt hydrolysis. Hydrolysis means water. The reverse of the neutralization is only called as a salt hydrolysis. On salt addition of water, what type of acid it is giving, what type of base it is giving, based upon that, they are divided into four types of salts. Okay. So SASB, strong acid, salt of strong acid and strong base. Okay. Here, salt of strong acid and strong base. That means it will not hydrolyze. This side only it will be because both are strong. Okay. Once there is a weak anything, then only reversible is there. Then only some constant will be there. Okay. Here the reversibility is because of the weak acid and strong base. Okay, so weak acid will undergo hydrolysis, that is anionic hydrolysis. What type of hydrolysis it will undergo? Acid is anionic hydrolysis. Okay, type of hydrolysis they will ask you many times they are asking. Okay, same way weak base. So here base is weak, therefore instead of anionic, what it is going to be? Cationic hydrolysis. If both are weak, both anionic and cationic, both anionic and cationic hydrolysis, both are possible. Okay. Now coming to this hydrolysis, like degree of dissociation, we talk about the salt for hydrolysis, degree of hydrolysis. What is H here? Degree of hydrolysis. Okay. H degree of hydrolysis is formulated like this. Kw. What is Kw? Ionic product of water. Here acid is weak. So base is strong. There is no Ka. Ka and Kb are only for the weak substances. Okay. So acid is weak. Therefore Ka into C. Here base is weak. Kb into C. Kw and C both are common. Okay. And most important thing is here there is no C because both are weak. Acid is also weak and base is also weak. Ka into Kb. Square root is common. Memory technique, is it understood? If acid is weak, write Ka. If base is weak, write Kb. If both are weak, write both and delete C. Is it understood? But square root and Kw are common. C is also common. Okay. This is the formula for degree of hydrolysis, how much of the part of the hydrolysis took place. Okay, so then hydrolysis constant, simple Kw upon Ka for weak acid. Here base is weak, Kb, both are weak, Ka into Kb. Is it understood? Now come memory technique to remember pH also. Okay, so more formulas, more confusion, less marks. But with the tricks, more formulas, more tricks, more marks, more accuracy. Understood? See here, weak acid and strong base. So base is strong, so pH will be more than 7 or not. So more than 7 means plus. What it should be there? Plus. Okay. Acid is there Ka. So Ka. Acid is there, that's why Ka, and here it is plus and plus log C. C is what? Concentration of acid. Same way, strong acid and weak base. So acid is strong, pH will be less than 7. To make it less than, what you have to do? Minus. Minus. See here, minus and minus. And base is weak, pKb. Okay. Salt concentration is same. Y minus, Y plus, is it understood? Base is strong, so pH will be greater than 7. So plus and plus. Acid is weak, that's why Ka. Base is weak, that's why Kb. And here less than 7, that's why minus. Okay. So when both are weak, we cannot say it is less than or more than. Okay. So acid wanted to increase the pH, base wanted to decrease the pH. So acid plus and base minus. There is no C term in case of the both are weak. Salt hydrolysis and how to remember the so many formulas. Memory techniques for salt hydrolysis formulas. I think it is understood to everybody. Okay. Okay, next we are into the next topic, buffer solution. What is the next topic? Buffer solution. Okay, buffer solutions are special type of solutions. Buffer solutions are what? Special type of solution which don't change their pH, which resist change in pH on addition of small amount of acid or base or water. Okay, so if you people are feeling any tiredness, if you are feeling very bored, then please take a break, refresh yourself, pause it here itself, go and refresh yourself. But you have to maintain your stamina, you have to maintain your interest in the subject till last part of the video, because up to last part every point is important. Okay, so don't lose your interest after 10 minutes, after 15 minutes, whenever you feel. It is a normal human tendency. Okay. So if you're feeling tiredness, then take a break, take a pause, then go for break and come back with the same energy, same josh. Okay. And keep studying up to the last, because it is very highly important chapter, lengthy chapter, difficult chapter. Important, lengthy, and difficult, all are with this chapter only. Okay, so buffer solution is a solution which resists change in pH on acid, base, or water. This is what every book says and every student studies, but nobody will ask, sir, what happens with other solutions. Okay, in other solution other than the buffer solutions, when you add acid, pH will decrease. When you add acid, pH what happens? Decreases. When you add base, pH will increase. When you add water, pH will again increase. Okay, so in normal solution, when you add acid, pH will decrease. When you add base, pH will increase. When you add water, pH will again increase. In any solution, if does not happens any of them, then it is called as a buffer solution. Okay, so buffer solutions are basically divided into how many types? Two types: simple buffer and mixed buffer. Suppose weak acid. Weak acid is an example of simple buffer. Weak base is an example of simple buffer, but they are having less capacity to resist the change in pH. For a better buffer activity, we have to use a mixture. Okay, so there are two types of mixed buffers: mixture of weak acid where plus salt of weak acid with strong base. Okay, here weak acid, let us take acetic acid is a weak acid. Acetic acid is a weak acid, but when it is added with strong base, that is CH3COONA, this is the salt of the weak acid plus salt of the weak acid with strong base. Okay. Same way for this example is going to be, let us take NH4OH is a weak base. Okay. And when you add it with the salt for the NH4Cl, okay, This mixture is called as a mixture of weak base and salt of weak base with strong acid. This complete it is called as a mixed basic buffer. This complete it is called as a mixed acidic buffer. Acidic buffer and basic buffer are example of mixed buffer. Okay. How to find out formula for this? I am going to tell you. Okay. Maintain George. Okay. For finding out buffer pH, buffer POH. There are equations called as a Henderson equations. Okay. For acidic buffer, pH value we will find out. For basic buffer, POH value we will find out. Okay. So for acidic buffer, pH is equal to pKa plus log of concentration of salt upon acid. For basic buffer, POH is equal to pKb plus log of salt upon base. Okay. These are the two formula used for. Sometimes it is also called as a salt, can also be called as conjugate acid. What it is called as? Conjugate acid. And here it is called as a conjugate base. So don't worry about the conjugate acid and salt. Both are same. Conjugate base in the basic buffer is also called as salt. So with that you can understand that salt and conjugate base are same for basic buffer. Salt and conjugate acid are same for the acidic buffer. Okay, is it understood? And there is a topic called as a buffer capacity. There is a topic called as a buffer capacity. Okay, up to what up to what extent it can resist the change in pH is measured with the buffer capacity. Okay, how much change in pH took place per mole of the acid, equivalent of acid added or equivalents of the base added. What is buffer capacity? Amount of the change in pH took place upon amount of the or number of equivalents of acid or bases added for such change. Okay, that is called as a buffer capacity. Higher the buffer capacity, higher will be its nature as act as a buffer tendency. Understood? Better buffer capacity, better is the buffer solution. Okay, that means it can change, it can resist the change in pH for a larger duration, for a larger value of acid, for a larger value of base, for a larger amount of water. Okay. Okay, now we are into the most important experimental topic, titration and indicator. Okay. So first of all, titration is a general topic. The method of finding out the concentration. The method of finding out the concentration of a unknown acid or base. If acid concentration is unknown, base concentration must be known. If base concentration is unknown, acid concentration should be known. Okay. So here I am considering that acid concentration is unknown. Okay. Its concentration I want to determine. For that, what I will take? I will take a base whose concentration is known. I will take a base whose concentration is known. Okay. So that here I will fix the volume of this. Let us take 25 ml or 20 ml. And I will keep on adding the base. Acid plus base. What it will form? Salt. If I still some more base I will add, then it will become as a basic solution. Okay. So exactly the point where complete acid is neutralized by the base, it is called as a equivalence point or end point. What it is called as? End point. Okay. So when all acid available here is completely neutralized by base, then that point is called as end point. After that, if I add, then the solution will turn from neutral to base. Initially, what it will be? Acid. At the end point, what it will be? Neutral. And after end point, still if I am adding, it is called as a basic. Okay. So there is a change in medium. So when I put indicator into this initially, indicator is in the acidic medium. So then keep on adding the base, acidic strength decreases, therefore indicator color also fades away. As soon as the extra base is added, the complete solution will become as a base. So there is a color change. That means the main criteria, main characteristics of the indicator should be, it should possess how many colors? Two colors. In acid medium, one color. In basic medium, another color. And both should not be same. And it is not necessary that both should be colors only. Okay. If suppose in acid it is blue color, base it can be colorless also. In acid it is colorless. In base it can be anything, but both should not be same and both should not be colored. Okay. So if one color is there and the other should not be different color, other should be different color or even transparent is also okay. Okay. So that is about the indicator. Indicators are not any new substances. They're only extra criteria, extra characteristics that they should have different colors or transparency in different media. Okay. If an acidic media transparent, it should not be a transparent in basic media. If it is basic media blue color, it should not be blue color in acidic media. Anything other than the blue color is okay. So that is the indicator. At equivalence point, equivalent moles of acid must be equal to equivalent moles of base. Both should be same. Okay. So that is about the titration of indicator. There is no new formula, same formulas only. N1, M1, V. Okay, this is equivalent factor of acid, molarity and volume of acid is equal to equivalent factor molarity and volume of base. Okay, so this is about the ionic equilibrium. Thank you for being with me, and I suggest you to do this revision in 2 to 3 times and 2 to 3 shifts, so that effectively you should be able to study. Bye bye. See you. Keep watching which can enhance your knowledge, score good, and settle in your life with a bright career. Okay. Bye.